Yeah, so as a simple example, we will look at the simplest simplest case. This is the case of C2. And actually now we need some discussion about the name. So we saw the name Higgs branch. Hypermultiplet moduli space is another name. Sometimes people call it hyperkähler. Moduli space. This name is not good because hyperkähler moduli space typically refers to smooth, compact manifold, whereas the moduli spaces that we deal with when we encounter supersymmetry H-theories are non-compact and singular. So this name should be replaced by symplectic singularity. That's one of the reasons I, instead of talking about the hyperkähler moduli space that people used to say, let's say 10 years ago, instead I prefer to call it symplectic singularity because it reflects the nature that there is a singularity, and soon we will see why we also call it. Now, a mathematical name would be holomorphic symplectic varieties. And actually, when we look at all possible names, that's going to be the most suitable name out of all. So that's going to be the most suitable name that will be used in the analysis that we are doing, just because of the way the supersymmetry is okay, so we will do the simplest case. We will put coordinates Z1 and Z2 on C2. And so those are holomorphic coordinates. The symmetry on C2 is SO4, if I think of 4 real coordinates. And it acts on those coordinates in the following way. There is an SU2 cross SU2. One of them is an SU2R, and the other is just a global symmetry, so I'll have no label to it. And we can assign transformation laws to Z1, Z2, Z2 bar with a minus sign, and Z1 bar. They will carry weights 1, -1, and 1, -1 under those 2 symmetries, where R symmetry acts non-holomorphically on the coordinates, and this global symmetry is going to act in this direction, right? So SU2 and SU2. Now, because of this structure, we see that if I deal with holomorphic functions, I look at the highest weights of the SU2R. So, for example, if I look at the coordinate Z1 squared, Z1 squared will have non-holomorphic partners under the action of SU2R. So Z1 would be replaced once by Z2 bar, and second time by Z2 bar, then we form a multiplet under SU2R. But if I only restrict to holomorphic functions, then I will just have the highest weights under SU2R, understanding that in order to construct the complete supermultiplet, I will just need to act with the SU2R, and it's enough, it's sufficient to consider the highest weight under SU2R. So we are going to work with holomorphic functions in the two variables Z1 and Z2. And those holomorphic functions have these weights, 1 and -1. So the next thing to do is to introduce a Poisson bracket. So for this reason, the mathematical name would be Poisson manifolds or symplectic manifolds, because for this Poisson bracket there is a symplectic form. And so that makes a connection with the symplectic geometry, even though when you deal with symplectic geometry, there is no necessity to work with holomorphic functions. And this word, holomorphic and symplectic, just implies that we are going to deal with both holomorphic and symplectic. So the Poisson bracket will take this form. Let's take the convention Z2, Z1 equals to 1. And now, if I assign weights, so let's assign degree 1 to Zi, then the Poisson bracket is a bilinear form which takes degree 1 here and another degree 1 here and gives degree 0. Right. So the Poisson bracket has a weight of -2. Okay. So because of that, if I take a function of degree R1, another function of degree R2, then this will be giving me another function which has degree R1 plus R2 minus 2. Okay. And because of that, we see that the functions of the degree 2 form the algebra. So let's now compute the Poisson bracket of Z1, Z2. First of all, let's write the holomorphic functions in Z1, Z2, degree Please ask questions.
So any linear algebra is possible, right?
Yeah, finite dimension. So the holomorphic functions of the grade 2 will be Z1 squared, Z1, Z2, and Z2 squared. Okay. So let's compute the Z1, Z2 Poisson bracket with Z1. And because of the convention that we choose, where did I pick it? Over here. Because of this, I will get that this is Z1. Okay. And if I compute it with Z1, Z2, then I'll get minus it. Okay. So this function takes the function Z1 and returns it with the weight 1, whereas it takes Z2 and returns it with the weight -1. And so they measure the weight under the global symmetry. Okay. And furthermore, if we compute the Z1, Z2, Z1 squared, it will give me 2 Z1 squared, Z1, Z2 with Z2 squared, give me -2 Z2 squared, and Z1 squared and Z2 squared give me 4 Z1, Z2. Okay. So that's a simple computation. Check if I'm not making any mistakes, but that's what's going to happen. And from this, we see that we are forming an SU2 Lie algebra. Okay. Where the diagonal element Z1, Z2 measures the weight. If I take Z1, Z2 and compute it with Z1, Z2, it will give 0. And so I see that those are the 3 generators with weights 2, 0, and -2 of an SU2. So the functions at weight 2 are very important because they form a Lie algebra, and furthermore, it acts on the space of functions, and it's the symmetry of this space. In physics, in the gauge theory, we will call it the global symmetry of the corresponding modular space. Any questions? So now we can extend it to Hn C2n. So this is the quaternionic space. If I put coordinates Z alpha, then the Poisson bracket will be Z alpha, Z beta is minus epsilon alpha beta, and epsilon alpha beta is the invariant tensor. Now, as an exercise, compute the grade 2 and find the symmetry and the generators. Going to be positive weights, negative weights, and the elements which measure the weights. Is this clear enough? Too fast, too slow? Okay, so let's now apply this thing to Higgs branches. And let's take the simplest possible quiver. It's studied quite a bit. This is a super QED. And so U1 with n flavors and electrons. This is the way we denote the theory. We're using a graph. The graph contains two objects, nodes and edges connecting them. Nodes can come in two types, circle and square, gauge symmetry, flavor symmetry, and edges denote the matter fields of the gauge theory. And I hope this is sufficient to describe the gauge theory. Do we all know supersimilar gauge theories?
Well, you can explain what the line is.
So, so we don't know supersimilar gauge theories.
We know. I mean, in the audience, there's no question. You can continue.
So, in order to take this theory represents a Lagrangian. And the edge gives rise to two fields, which we can denote as Q for quarks, but those are really electrons. And they have two labels. Well, this is a U1 theory, so I will not have a label. Let's put the Qi for the electrons and Q tilde I from 1 to n for the super positive. Now, those are chiral multiplets with charge +1 under the gauge symmetry and charge -1 under the gauge symmetry. There is a superpotential, which I read from the quiver. And it takes the form of phi, where phi is a scalar field. If I'm in 4 dimensions, it's a scalar field, complex scalar, times Q I, Q tilde I. If I'm in other dimensions, we'll have to extend it, but the most convenient way to characterize the Higgs functions is to use the 4-dimensional description under the understanding that as I vary from one dimension to another, most of the time Higgs functions don't change, but there's a comment to that as well. So phi is a member of a vector multiplet, and the Q's are members of hypermultiplets. So the interaction is of the type, it's a trilinear vector hyper-hyper. From this, we have an F-term equation which says that Qi tilde is equal to 0. So that's the variation of the superpotential with respect to phi. So those are the vacuum equations. And I can write down a matrix M and with label I and J, which will be Qi, Q tilde J, like that. I mean, to be fair, I will have to reverse the order. It's not important for the abelian gauge theory, but once we do a non-abelian gauge theory, we'll have to be careful about the ordering. So I'll write it as Q J tilde Qi, like that. And then we find from the F terms that trace of M is equal to 0. So M is an n by n matrix, n by n, with complex entries, has 0 trace, and it squares to 0. And because it is made out of quarks, it also has a rank, which is at most 1. Okay. So the Higgs branch is the space called matrices n by n, such that they have 0 trace. They square to 0 and 1. Okay, so I can write it as a set of conditions. This is called the nilpotent orbit of SLN. And because of those conditions, it's actually the closure of the minimal.
Is it coincidence or is it a deeper meaning?
As long as I don't have baryons, most model space, many symplectic singularities are not. But there are plenty which are not. So you just need to compute. I wouldn't call it a bigger. When you consider the family of symplectic singularities, they are characterized according to different classes of symplectic singularities. One large class is the class where I have a nilpotent orbit of a finite dimensional algebra. And those show up in many gauge theories. Many times the gauge theories will be of quiver type, so collection of gauge groups with some matter fields. There are other classes of symplectic singularities that they would also show up in supersymmetric gauge theory. So it's just the simplest. It's the simplest. You see what happens. Now let's compute the functions of degree 2. So if I assign degree 1, so what is degree 1? Degree 1 are the quarks themselves. I have n quarks and anti-quarks, or electrons, anti-electrons, and if I assign degree 1 to them, what does it mean that they are degree 1? It means that they sit in a hypermultiplet, and by the construction of a hypermultiplet, going back to the simplest representation, which is possible, the hypermultiplet contains two chiral multiplets. Each of them has R charge 1/2. So the scalar field will carry R charge 1/2. And this will translate into those weights, plus minus 1 that we wrote over here. And so degree, it's natural to assign degree 1 to those hypermultiplets before we look at the space of gauge invariance. Now, once we assign degree 1 to Q and to Q tilde, one here and one here, then functions of degree 2 are just the ends.
There's a question in the audience. If you add Rak-Kyeong term to the superpotential, how does the Higgs branch change?
For this particular case, it will become a smooth variety. So I will deal with the singular varieties most of the lectures. There is a mathematical question of asking whether singularities can be resolved or not. This goes under the name of symplectic resolutions in the context of symplectic singularities. It's a nice study. It will show up as a gauge theory because it's a physical effect. You just add the Fayet-Leopolov term. But it's too early to discuss those things, and therefore I will not talk about them so far. So we will stick to the case where the varieties are singular and non-compact. Does this answer the question? Very good. Okay. So the functions of degree 2 are Mij. And as we said, they should transform in that representation. Is it clear why they should transform in that representation? And and we can identify which representation it is. It's written in the quiver. This is the joint representation of SLN. In the physics language, we typically, when we formulate the theory, we talk about the real compact subgroup of SLN, SUN. So this is just the complexification of the flavor symmetries, and this action of complexification is a very natural procedure which happens as soon as I put 4 supercharges. Right? So many times I will talk about the complexified flavor group or gauge group, but you could also think about the real part, the difference between the fact that I'm working with a supersymmetric. Any questions? So now we can compute the Poisson brackets. So I'll just put it as an exercise. of the generators of this modular space. And from here, we see that those two chiral multiplets, they form the space Hn. They are coordinates on Hn. It's the same n. So you could think of them as one class of coordinates and another, and therefore they will have this particular Poisson bracket, which by convention I can pick to be Q tilde J Q I B delta H. Where again, as before, delta Ij is the invariant form on SL. I gave you this. Now it's you could just compute this. Any question?
So in principle, I could do this for any fixed point orbital space which does not have baryons.
No.
No.
The way you formulate it is not good. You can do it for any Higgs. Now, given the tools that I gave you, you can do it for any Higgs function,
Right.
regardless of whether it's a nilpotent orbital. Because what do I need? I need the quiver, and I need the Poisson bracket, and the rest follows. So the next thing to do is to compute the Hilbert series. So let's just start with the H n equals to 1. And we said we have two coordinates, z1 and z2. The set of all holomorphic functions is going to be characterized by this function, h of t1 and t2.
There's a question in the audience. Why is SLN not SUN? The Q's are complex, right?
So they missed the explanation I gave just before. Maybe they didn't hear. So in a field theoretic formulation of the Lagrangian, we as physicists we pick the compact real subgroup of SLN. And when we introduce supersymmetry, this SUN gets complexified to SLN. And now this is a standard material in a supersymmetry class. Do you want me to go over the arguments there?
No, thanks, Ami. That's what I thought.
Okay.
There's another question.
So there are in a hypermultiplet there are two chiral multiplets with opposite charges. So if it's the fundamental here and charge -1, then the other one will be charge +1 and anti-fundamental. Right? So those are the two. So when I write an edge in a quiver, I should think of two sets of complex matrices. I have K and N. I'll have a matrix which is let's put a label, gauge label, which will be alpha, and the flavor label, which will be I. So alpha K and I 1 up to N. So this is a rectangular matrix of quarks, and then there will be a conjugate or an analogous chiral multiplet, which will have the opposite labels. If this is fundamental anti-fundamental, then this is anti-fundamental. Now, the labels Q and Q tilde are just random labels. You could call them A and E, whatever letters you wish to pick. The important thing is that those are rectangular matrices, which are parameterizing the copy of the quaternionic space to the power k times n. Is this clear? Does this answer the question?
Does this answer the question? Is it not? I think so, yes. So how does this rely on the choice of 3D n equals to 2 subalgebra from the 3D n equals to 4 supersymmetry?
So it's a mistake to think about subalgebras. That's a misconception that I see many physicists do. We are not doing anything about subalgebras. We are just putting we had, so I erased this. No, it's here. Holomorphic and Poisson brackets. So I need to pick a complexification. If I have 4 real coordinates, I can complexify them in a certain way. I can declare which pair I pick and form into one complex variable, and the other pair will be another complex number. That gives me the notion of holomorphic. And then in addition, I add the Poisson bracket, and that's it. No choice of a subalgebra. You'll get into trouble if you think in this way. Okay, I hope this is clear. What we are doing here is to rearrange the coordinates in a way which is holomorphic and symplectic. Now, I know that it's difficult for many people because for many years they have been using this misconception. So it's going to be quite a process to get rid of that. But just think of complexification and Poisson brackets. Does this answer the question?
Yes.
Okay. So T1 is going to be a fugacity which counts the number of Z1s, and T2 is the fugacity which counts the number of Z2. And we just write this expression. So this expression would count all possible homomorphic functions on C2 in this way. And what I do next is to put the degrees. T will be the R charge. So this is the highest weight under C2R. And the X will count the weight under C2, the global symmetry. And when I write it in this way, I'll get 1 over 1 minus x, 1 minus t over x, which upon expansion gives me this expansion n times t to the n, where I write the character for an SU2 representation of highest weight n is x to the n plus x to the n minus 2, going down by 2 until I reach x to the minus 8. Any questions? So this is known. Good. So, but we also saw that those weights here, when I compute the Poisson bracket of Z1 to the I, Z2 to the J, this will give back Z1 to the I, Z2 to the J. And because of the way we chose the Poisson bracket, Z1 will have positive contribution, Z2 will have negative contribution, so I'll get I minus J. Right, so that's going to count the weight under the flavor symmetry, the SU2. Okay, so those are the powers of X that I get when I do this expansion. Any questions? Okay, so we can now write the formula for the Higgs branch. Hilbert series. What I need to do is to take all possible symmetrizations of the hypermanifolds that I have. So this I will get by using the PE. We know about the PE. So I will have the quarks, the Qs, the 2 theta. I will denote a representation of SUN or SLN. It's the same. 1, 0 with power T, and charge Q minus 1 plus the anti-fundamental. So those are the Qs, the Q tildes. And I have an F term, which is invariant under SUN and carries R charge 2. Right? Because that's 1, that's another 1. So minus T squared. Closing the P. So matter field matter fields, F-term relations. They will transform in the adjoint representation. But since here the gauge symmetry is U1, the adjoint representation is trivial under U1. And now I will take a hard measure integration, but since I'm only having a U1, it's going to be a trivial thing. Okay, so that's the way I'm going to compute the X branch. And it has a natural generalization for a non-abelian cage. Do I need to write it down or is it clear? Okay. So that's how we get symplectic singularities. Now let's extend the exercise to K and N. And again, stick to Higgs branch. So the discussion goes through. Now my quarks will be Q tilde, alpha I, Q alpha I, those guys that we wrote over here. And I have meson states with labels I and J in the adjoint representation of the flavor symmetry, SUN. So M is an SLN matrix. Tilde I alpha, alpha J. So those are the mesons. Functions of degree 2 and functions of degree 2 transform in the adjoint representation of the flavor symmetry. Again, I can write down Poisson brackets and compute the way those functions act on other. From the F-term relations, which are Q I alpha, and I need to sum over flavor indices. So it will be I here, that's a tilde, and beta. Remember that this transforms in the adjoint representation of the flavor symmetry, which is UK, of the gauge symmetry, which is UK. So this is the F-term equation. And these are adjoint values, but the adjoint representation of the gauge symmetry. This is the adjoint representation of the flavor symmetry, adjoint representation of the gauge symmetry. And using this, I will conclude that trace of M is equal to 0, M squared is 0, and rank of M is at most 1. And so this is the closure of the minimal nilpotent orbit of SLN. Any questions? I hope you could repeat all of those computations. Some of them I skipped. Okay, so this is the moduli space. So for you, Rak, that's another example. Instead of, sorry, no, I just got it wrong. No, you have to correct. The rank is not at most 1. The rank is at most K.
Yeah.
And now it's no longer the minimal nilpotent orbit.
Yeah.
of a nilpotent orbit of SLN, so this is correct now. But nilpotent orbits are characterized by partitions of n, and so the precise partition is 2 to the k 1 n minus 2k. So for k equals to 1, it is the minimal nilpotent orbit, and for k higher than 1, it's a different nilpotent orbit.
What does the partition?
Precisely this. You could also pick an element. So if you open math discussions on nilpotent orbits, they will tell you that you pick an element which is nilpotent, which satisfies those things. So you could take an element which has zeros in the diagonal. You'll have k1s here, and then the rest are 0. So let's look. The trace is 0. This is a Jordan block here of size k by k, therefore it will square to 0. This is satisfied. The rank is at most k because I have k columns or k rows of non-zero entry, and that's it. Now, if I will so that's an element. This is an element in this space. And if I conjugate it by an SLN, by a joint action, so multiplied by an SLN matrix on the left and the inverse on the right, then I could get many elements. And by conjugation, it's a similarity transformation. So this is invariant, this is invariant, and this is invariant. So by doing this conjugation, I get all possible of this type. I also need to be careful about this condition here. If the rank is at most k, you need to be attentive now. If the rank is at most k, then the rank can be 0, 1, 2, all the way up to k. And this doesn't show up here. Right? This is the set of all matrices which have rank precisely equal to k, not less. How will I get something less? I can do a similarity transformation, and I can focus on one of the elements to be very small, but it will never be 0. So the rank will always be k, but if I take the closure, then I could reach lower cases. And so this moduli space here, because the rank is at most k, is the union of all cases where the rank can be either 0, 1, 2. 0 is the 0 matrix, and this is the minimal orbit. This is the next to minimal orbit, and so on. More questions? But a nice thing that a simple quiver, one way of calling this quiver is a framed A1 quiver, right? Because the linking diagram formed by the gauge nodes is the A1 linking diagram, and it has flavors. It's a framed A1 linking diagram. And physically, we would call them SQCD theories with gauge group UK, not SUK. UK, no bios. And it's nice to see that a well-studied family, SQCD, with UK gate symmetry, gives rise to the family of nilpotent orbits, and this repeats itself. It's not the end of the story. We just need to go over a collection of equivalents and figure out what are the moduli spaces.
How about the analog of AN?
So if you take A2, let's take A2, then I have 4 numbers to choose, K1 and K, let's pick this to be K1, K2, and framing N1 and N2. So I have 4 numbers, and we would call it framed A2 linking diagram, because that's the structure. The moduli space, most of the members of this family are not closures of nilpotent orbits. They are just moduli spaces, but they are called, they have a name, they're called slices in the affine Gassman. But for this, we will need to introduce some more things, and we are not yet ready to do that. Okay. We just need to develop more formalism. Just as a teaser, this is going to be. So one of the aims this lecture series that eventually will know what this is. More questions. Okay, so we wrote down the Hilbert series, and the Hilbert series would give me a collection of data, so I can extract the dimension of the moduli space. I can extract the generators. So for nilpotent orbits, we see in those 2 examples, the generators of the ring of functions on the Higgs branch are in the adjoint representation. And if I generalize from 1 to K, this remains the case. Now, this is not a trivial statement, but I'm telling you now. Just need to check either by computing the Hilbert series or by using the Poisson balance to find that all holomorphic functions on the moduli space will be generated by the adjoint. Another point is that all of those chiral operators. So these are chiral operators. This is a product of chiral is chiral. Where when we discuss the moduli space, I have a correspondence between a chiral operator and a holomorphic function. And so when I count holomorphic functions on the moduli space, I also count operators in the chiral. So that's the physical counterpart of what we are doing. And we are, this function of the Hilbert series gives me a trace over or an accounting of all possible chiral operators. They are protected operators. They break half of the supersymmetry. And the is generating functions which count operators, but also be careful that we are not introducing any derivatives. Right? So we are just counting holomorphic functions on the model. Yeah. So the question was to compute the dimension of the moduli space from the Hilbert series. So, so the dimension of the moduli space, I take a Hilbert series, which is a function of the fugacity for the highest weight of S2R, and a collection of other fugacities, which we can denote by xi. So those are the, so this is S2R, highest weight under S2R, and those are the fugacities for the global symmetry. What I do is to take the function when all of them are equal to 1, but leave the R symmetry. And now what I do is I take the limit t equals to 1. At t equals to 1, the function will have a pole. So it goes like some number, c, divided by 1 minus t to the power d. And d is the dimension of the moduli space, the complex dimension. As you could see over here, right? I take this function here. I set x to 1. Now I have a pole for the 2 at equals 1, and that's the dimension of C. And this is an expression which works all the time. And there is also a meaning to C. But we'll know. More questions?
There's a question in the audience. If you vary the complex structure in the CT1 family of complex structure in the hyperkähler structure of the Higgs branch, how will the holomorphic Poisson structure change? Will the symplectic singularity persist with respect to the different symplectic structures?
Yeah, it will be a symplectic singularity for any choice of them. I don't see any advantage of doing this. But the answer is yes. So I'm not sure, what are you after? I mean, you could ask your question on H, right? This is already can be answered on H. Suppose that I have 4 coordinates, and I could just play with the way I complexify. So everything that we said goes through. You could just check it. Just be careful that when you are dealing with the Poisson brackets, you're dealing with the Poisson bracket of holomorphic functions, not to involve anti-holomorphic with holomorphic. And be careful that you are picking, you know how to move from one complex structure to another. Just an SU2 rotation. So yeah, I mean, it's an exercise that you could do. I don't see any problem in doing that, but I also don't see the advantage. Any question?
I mean, how long do you need? 10 more
If
minutes?
you tell me to stop, I can stop anytime.
Well, let's do 10 more minutes and then.
Okay, so the next thing is to talk about the 3D n equals 4 Coulomb branch. We wrote down the Hilbert series for the abelian part, but I assume that doing it non-abelian will also be straightforward. So we can, I mean, if you want the details, we can do that. As I said, I don't like the name Coulomb branch, but this name just sticks. And you will see why I don't like the name Coulomb branch. I prefer the name magnetic construction, but let me just write, go back to the case U1 with N flavors, and then see how we can construct another symplectic singularity from the same quiver, right? So in general, when I have a quiver, there are two symplectic singularities I can construct. One will be the Higgs branch, and the other one will be this Coulomb branch. The way I prefer to call it is the Higgs branch is an electric construction, and the Coulomb branch is a magnetic construction. One is using weights, electric charges, the Higgs branch, and the other is using co-weights or magnetic charges for the construction. And so the way we will do that is to say, okay, first of all, there is a topological symmetry. We are on the in 3D n equals to 4. So in 3 dimensions, I can write down a current J equals to star F, and write down the Bianchi identity as a conservation law. So star of F is a conserved current. So for every gauge symmetry, 3 dimensions, every U1 gauge symmetry, there is a corresponding flavor symmetry, topological symmetry. So, and this topological symmetry does this job, counts magnetic charge, because if there is a non-zero contribution, something is charged under J, then it carries magnetic charge under the gauge. Any questions about this point? So there are charges, magnetic charges. Under the gauge loop. which become, which characterize Coulomb. In particular, there is the at Hooft disorder operator. Suppose that I take an operator defined at point X, and I take a two-sphere surrounding this, where I take space-time. This is 3D, so space-time is R3. In R3, I take an S2, which goes around, and I just make sure that the integral over F over this two-sphere is given by a charge. Let's call it M. So this is the definition of the host for the disorder operator. Whenever I have conserved the charge current, I modify the path integral. So when I write down a path integral and I integrate over all possible gauge fields, I put a boundary condition such that the this integral over that particular point, right? So there is a point, there is an S2 which surrounds the point, and the flux around this point is a precise magnetic charge. This would correspond to a disorder operator. So this gives me the existence of operators on the Coulomb branch which carry magnetic charges. Now, what I'm going to do is to assume that those operators are chiral operators. Of charge M. And we are going to call them VM. So a local operator, which is defined at a point such that when I go around, it measures magnetic charge. This is a definition by Prof for any conserved time. Right? Each time I have an instanton, I can define an instanton operator by picking a point and going around and integrating and measuring the number. Right? So it gives rise to a collection of operators which carry charge whenever there is a conserved charge. So VM. In addition, I'm going to have phi. It's the same phi that we saw when we wrote down the superpotential. And those are the set of chiral operators. M is a magnetic charge, whereas I could take phi to any power where k is any non-negative integer, because I'm looking for operators which are holomorphic, right? So I don't allow for negative powers. So this is the Coulomb branch. It's the space of rest monopole operators. Again, I'm going very quick on these things, and perhaps this is also the time to break. I just need to provide multiplications on these things, but it will take some time. So perhaps this will be our starting point. So I'm going to think of the Coulomb branch as the space of monopole operators, and remember this way of thinking about it. And I prefer to talk about the moduli space as the space of Brest monopole operators rather than to call it the Coulomb branch. Okay, so we will continue next time.
Okay. Any quick questions on Zoom or in the audience? So we will continue the lecture series. So tomorrow at 4, we will give a special colloquium. The story will continue, I believe. And then on Friday, we will continue with the lecture series at 10 o'clock Korean Standard Time. Okay, so both also in the audience, please join us, and thank you again, Ami, for the lecture today. Thank you.